Hi, everybody. It's me, Dr. Gray. I wanted to talk to you about the assignment that y'all have been given. This first assignment is all about using the software, this free software known as protein purification. And really, what this is boiling down to is asking you to kind of get familiar with the general process of protein purification and simulating it with this tool here. So on your worksheet, you're prompted to select a particular mixture of proteins that you want to separate from one another, or from, sorry, a mixture, and from that mixture, you're going to separate a protein. And so I'm going to walk you through basically some of the early parts of this. So I'm going to start from the beginning, and I'm going to select a mixture. I'll go with this complex mixture. You're going to follow the directions that are on the worksheet that you have. Um, as to which mixture to pick. I'm going to select complex mixture. I'm given this information that tells me that this mixture has approximately 60 different proteins in it. It doesn't really matter which one that I choose. So I'm feeling lucky with number 55. I kind of arbitrarily selected that. Select one, click OK. And this tells me that this temperature is stable for several hours at room temperature or at temperatures up to 30 degrees Celsius and has a pH range. It's still functional between a pH of 3.5 and 11. So that's information worth noting because the first thing that I do is I'll click OK. I'm going to go to a heat treatment. Now, what this heat treatment does is basically it says, you've collected this protein mixture and you're going to heat it up, and for how long? I'm gonna heat this for 240 minutes, about 4 hours, 30 degrees Celsius. Whenever I click OK, what I'm gonna see is that nothing changes. The protein that I am trying to purify, well, it didn't really get purified. I can click OK because what this shows me is the yield of my protein is still at 100%. So I still have all of my enzyme in there. So I didn't lose anything. But if you look at this enrichment column, which I will use my annotate tool, this enrichment column right here, it shows me that it didn't really improve my standing with purifying this protein. So I'm going to click erase and close that off. The next thing that I want to do is go to separation. And here's where I'm going to do ammonium sulfate fractionation. And I'm just going to start with, let's be conservative. I'm going to start with 35%. So that means I have an ammonium sulfate solution that is 35% saturated. I'm going to click OK. And what this tells me is that I have precipitated 71% of my enzyme and 21% of the protein. Now, I can proceed with this in a couple of different ways. What I would really love to do is precipitate all of my enzyme and none of my protein. But this tells me that I've enriched for my enzyme. And so what I'm going to do is I'm going to use my precipitated material. I am doing this at the cost of nearly 30% of my enzyme. But if you think about it from the standpoint of what did I get rid of? Well, I got rid of 80% of my other protein. And I got that 80% from the 21% number there. So if I click OK, what I see is, and what I want to kind of keep an eye on, I'll click OK here. What I want to keep an eye on to basically affirm that I'm going in the right direction is I want to use this enrichment column because that tells me that I enriched for my enzyme. So I see 3.4. So anything above 1 is considered good. You're enriching for that protein. Below 1 is implying that you're not enriching for your protein. So I'm going to close that. And what I'm actually going to do at this point is I'm going to do another ammonium sulfate fractionation. I think the last time I did 35%. I'm going to try 36%. Okay. And I've again enriched for my enzyme and I've gotten rid of some protein. I'm going to use my precipitated material and I see that my enrichment is at 4.1. Now, it's important to recognize that, well, where is my enzyme at this point in time? Not specifically like location wise, but purity and how much enzyme do I have? I have done these enrichment steps and my yield of my enzyme has dropped to 51%. So I've enriched, but it's at a cost or it's at the expense of losing some of my enzyme. So at this point in time, I don't really want to lose any more of my enzyme. And you can go any a number of different ways with this. what I'm going to do is I'm going to go to ion exchange chromatography. And ion exchange chromatography, if you click this info tab, that will provide an overview of ion exchange chromatography, and then it will go down to explain the different columns. So this paragraph says several side chain groups of the amino residues and proteins are ionizable. Lysine or glutamic acid are two examples. Lysine is a positively charged residue, and glutamic acid is a negatively charged residue. As there are N-terminal amino and C-terminal carboxy groups, therefore proteins are charged molecules. This characteristic can be used to separate different proteins by ion exchange chromatography. The two most commonly used resins for ion exchange chromatography are CM cellulose and DEAE cellulose. Okay, so this goes on to say that a CM cellulose has a CH2OH group or where there's a CH2OH group on a carbohydrate, that's been converted to a CH2OCH2COOH. So we're talking about a group that's ionizable, so something that can be negatively charged. And at a neutral pH, that group is negatively charged, which means that a CM cellulose column is a negatively charged column. So I'm going to go ahead and close this, and it goes on to elaborate and explain your other columns, but I'm going to go that CM cellulose column. That is a negatively charged column. So if my protein is positively charged, it will adhere to the column. I have no clue if my protein is positively or negatively charged. Now, this asks us to define the method of elution. And I believe that, okay, so at the very bottom of that info tab, it says use either a continuous pH gradient or a continuous salt gradient. And that's going to result in a high degree of protein fractionation on protein charge. In practice, one can use a stepwise elution. So this gradient is I'm gradually changing the concentration of a salt, or I'm gradually changing the gradually changing the pH of the solution. What I'm going to do is I'm going to select this salt gradient. So that means that I'm going to add a solution to this column that has a low salt concentration. And then that salt concentration will very gradually increase until it reaches the point where that protein is going to be released from that column. I'll click OK, and this asks for the pH of my buffer. This is where you need to think back to your enzyme. My enzyme was functional between 3.5 and 11, so a buffer pH of 7 is just fine. So I'll click OK there. Then it asks for the start of my gradient, 0 millimolar salt versus 0.5 molar salt. So I'm going to click OK. And here's what I get. Now this curve right here, the blue lines show where protein is, and the pink line shows where my salt concentration is. So if you look at basically the first, 30 some odd fractions, if you look at that pink line, that shows that the first 30 some odd fractions, I've got a salt concentration of basically 0. And there's one protein that elutes around 20. Now, that salt concentration begins to increase until from fraction number 33 or so all the way up to about 125. And you see a couple of proteins elute there. There's 1, there's 2, 3, 4, 5. Okay, so we've got all these fractions that elute. The question is, which one of them is mine? And that's actually, with this software, it's very easily answered. And the way that it's answered is by going to the Fractions tab and clicking Enzyme Activity. Now I need to clear all my drawings, and you'll see this one brilliant bright red peak. So what I can say about my protein is, well, I have a protein that basically elutes from my column, which is great. And it elutes after my salt concentration increases. Now, this peak right here, can I say anything about that? Well, one thing I can say is it's not my enzyme. Can I say anything about the charge of that protein? I absolutely can. I can say that because this protein eluted from the column without any salt present, well, then that protein has the same charge as my column. That is a negatively charged protein. Now, my protein of interest, well, it elutes right about here, where I see my salt concentration has gone up, and it hasn't gone up a whole lot, but that's whenever I see my enzyme elute from my column. So what you're going to do as a follow-up to this is do an SDS page. So I'm going to do this one-dimensional page under the Page tab. This is a technique that you can separate proteins on. And I'm going to select a couple of fractions. I'm going to select fraction number 20. I'm just going to try to select fractions that correspond to those blue peaks. So I'll click Add there. Then I'll go with, let's say, 42. Then I'll go with 45, 57, 62. Let's go with 67. And then go with 80. Click OK. Okay. Now, I'm going to hide this gel. My protein is right at about fraction number 40. Now I want to look at my, oh, darn. I'll just go ahead and do 20 and 42. Okay. 42. Aha. This is great. What I've got is here's a peak, or here's a band, here's a band, here's a band. I've got 3 bands. So I've taken my protein, that was one of 60 different proteins, and I've narrowed it down to 3 potential proteins. This is great. Now, what I can do as kind of a follow-up to this is I can go to this immunoblot, because if I look at an immunoblot, that's also known as a Western blot. And a Western blot is going to give me, it's going to tell me which is my specific protein. I have no clue which one is mine, but there are a couple of things that I can say before I look at that Western blot. One thing that I can say is this right here, this band at 50 kilodaltons, I don't think that's my protein, because that band is found in fraction number 20 also, where I saw no enzyme activity. So really, my protein, I think, is most likely this one or this one, because those 2 bands, I'm going to erase this one at the top, this one that's at 20 and this one that's at about 7 kilodaltons, those are the bands that correspond to approximately the size, that are uniquely found in fraction number 42. Now I'm going to go ahead and do my immunoblot. Aha, it's that one that's about 7.5 kilodaltons. At any rate, I think that this is a tool that's really helpful to conceptualize protein purification. We'll probably revisit this over the course of the semester a couple of different times, just so we can get a kind of a faster analysis of protein purification, the conceptual understanding of how to purify a protein. Well, I hope that was helpful, and I hope you have a wonderful afternoon. Bye.